Example 4. The graph of f prime of x is given below. In addition, we know that f of 0 equals 2. Use this information with the graph above to fill in the following table for values of f of x. Be sure to mathematically justify how you got your results. So here, we have this picture of the derivative. And we already know some relationships about the derivative and the original function. We know that if the derivative is negative, the original function is decreasing. If the derivative is positive, we know that the original function is increasing. But now, using the fundamental theorem of calculus paired with one data point, we can figure out exactly what the value of the original function is. And that's really powerful. So the key to this whole thing is that we know a value on the original function. We know the starting value, f of 0 equals 2. So we can use that paired with this picture to now find the values of the original functions at every point from 0 to 6. And that's really important because that means we could plot those points later and get an exact picture of the original function. We've spent a lot of time going from the original to the first derivative, but this is what's going to allow us to go in the other direction. So how do we use this? So what we want to do is we first want to figure out the value of f of x at x equals 1. We already know the value at 0. So the fundamental theorem, I'm going to come up above, says that if we take the integral from 0 to 1 of f prime of x dx, that's going to equal the original function at 1 minus the original function at 0. So what we're trying to solve for is f of 1, right? The functional value when x equals 1. So what do we already know? We know that f of 0 equals 2, right? That's given to us in the setup of the problem. And that's the piece we really need. So now, if we can figure out how much our function changes between 0 and 1, then we'll be able to find f of 1. So the change from 0 to 1, we can use the graph for. We want to look at the area between 0 and 1 under the curve here. So you can see that this is a nice little triangle here. So from 0 to 1, if we do 1/2 base times height, the base is 1 unit long because we were going from 0 to 1, and the height is -1. So half times 1 times -1 is -1/2. So this integral, the area, is -0.5. So to get f of 1, we're going to need to add the 2 over to the left. And if we add this 2 over here to this -0.5, we get that f of 1 equals 1.5. Now, if we want to find f of 2, we need to set up a new integral. But we're going to do it in a similar fashion. So up here, we have the integral from 1 to 2 of f prime of x dx is going to equal f of 2 minus f of 1. So the functional value at 2 minus the functional value at 1. Well, the functional value at 1 is what we just solved for. We know that that's 1.5. So now, if we can get the area under the curve, we can solve algebraically for f of 2. So from 1 to 2, we're looking at the area between the curve and the x-axis. And that's a nice little rectangle. So we're going to do base times height. My base is 1 unit long, and my height is -1. So 1 times -1 is -1. So to solve for f of 2, I'm going to need to add 1.5 over to the left to get that f of 2 alone. And if I add 1.5 to -1, I'm going to get 0.5 as my value at 2. So let's keep going. If I want to find my value at 3, I'm going to do the integral from 2 to 3. F prime of x dx is going to equal, by the fundamental theorem, f of 3 minus f of 2. We know the value at f of 2 because we just computed that. So now we just need to find the area under the curve from 2 to 3. So from 2 to 3, the area under the curve is again a rectangle. So it's going to have a width of 1 and a height of -1. So that area, again, is -1. So to solve for f of 3, I need to add the 0.5 over. -1 plus 0.5 is going to give you -0.5. So f of 3 is going to be -0.5. Moving on, to find f of 4, we're going to do the integral from 3 to 4, f prime of x dx. And that's going to equal f of 4 minus f of 3. F of 3, we know it's -0.5. And to find the area under the curve from 3 to 4, we again look at the area between the function and the x-axis. So here we get another triangle. Triangle is 1/2 base times height. So we have 1/2 times 1 times -1, which is going to give me -0.5. So here we have to be a little careful. So we have f of 4 minus -0.5. So the minus and the negative would cancel. So I'd have f of 4 plus 0.5, which means that I was bringing it over to the left-hand side. I have to do -0.5 minus 0.5. So when I do that, I'm going to get -1. So f of 4 is -1. And that should make sense because we were at -0.5 and then we were subtracting off another 0.5, right? We were adding more negative area. So it should become more negative, which it does here. So now to get the value at 5, we're going to do the integral from 4 to 5 f prime of x dx, which is going to equal the original at 5 minus the original at 4. And we know the value at 4. We just found that. That's -1. And so in order to get the area under the curve, we look at what's happening between 4 and 5. And something interesting happens here because now we're above the x-axis, right? We've crossed the point where now our area is going to be positive. So when we calculate that area, we're still looking at a triangle. So we do 1/2 base times height. My base is 1 unit and my height is 1 unit. So 1/2 times 1 times 1 is positive 1/2. So that area is positive 1/2. And I'm going to bring over the -1. So I have -1 plus 0.5, which means that my functional value at 5 is going to be -0.5. So finally, last but not least, we need to find f of 6. So we can do the integral from 5 to 6 of f prime of x dx equals f of 6 minus f of 5. So f of 5 we know is -0.5. So here, let's do this one all the way out so you can see where the negatives cancel. So we have minus -0.5. Now the area under the curve from 5 to 6, that's a rectangle. It's going to have a base of 1, a height of 1, so a value of 1. Here, the negatives cancel. So in order to bring this over, we have to subtract 0.5 from both sides. So it'll cancel on the right, and I get f of 6 equals 0.5. So now, because I used the fundamental theorem for all of these values, I have all of these points on the original function that I can use to then draw the picture of what's happening. So I'd plot the point 0, 2, the point 1, 1.5, the point x equals 2, y equals 0.5, the point x equals 3, y equals -0.5, so on and so forth. And what you notice here is that from 0 to 4, my function is decreasing because you see the numbers 2, 1.5, 0.5, negative 0.5, negative 1. Those are decreasing. And that's exactly where my derivative was negative, and I had the negative area. And then from 4 to 6, my numbers were increasing, negative 1, negative 0.5, positive 0.5. So we see that the derivative was positive and that the area was positive. So now I have precise points on my original function, so I could plot those points and get a pretty good sense of what the graph of the original function is if I wanted to. But again, the key to this whole thing was having this starting information. That's what allowed us to use the fundamental theorem, and that's what started this whole process. From there, we were just estimating these areas and adding them along as we went. So let's look at one more example. Example 5. Suppose the velocity of a moving object is given in the graph below. So let's take a minute to talk about this graph. We can see that time is in seconds, and the velocity appears to be in meters per second. So we have some object that's moving. For the case of what we're going to be studying here, let's assume that positive movement means that we're moving away from a base, and negative movement means we're moving back towards the base or in the other direction. So you can also think left and right. So maybe positive moves to the right, negative moves to the left, but you should think about some sort of directionality in your mind when we start talking about this. So part A, describe the motion of the object over the first 10 seconds. So let's look at where that 10 is. So what I notice is that some of the area between 0 and 10 is positive, and some of the area is negative. So that looks like it changes around time equals 4. So between time equals 0 and time equals 4, we are moving, let's say, forward. We're going forward. We'll count positive as forward. And from time equals 4 to time equals 10, we're going to be moving backwards because it's negative. We could also figure out how far forward and how far backwards if we wanted to approximate the area under the curve. So real quick, from time 0 to time 4, I have a triangle here. So if I do 1/2 base times height, my base is 4 units, my height is 4 units. I multiply by half, and I get that that area is 8. So here, not only do I move forward, but I know that it's 8 meters forward. If I wanted to find the area underneath the curve, I'm going to break this up into 2 pieces so that I have a rectangle and a triangle. So my triangle goes from 4 to 8, so that's 4 units for the base. And again, that comes down to -4 for the height. So 1/2 base times height gives me -8 for my triangle. And then my rectangle is 2 units by -4 units. So that's another -8. So I moved forward 8 meters, and then I moved backwards -16 meters. So I was going back in the other direction, -16 meters. So I can get that information exactly because my graph provides values on the x-axis and y-axis. Part B wants to know, what is the acceleration of the object during the first 8 seconds? So time equals 0 to time equals 8 is this line that starts at 0 and decreases all the way until 8. So this line here. And so we have the graph of velocity. And remember, acceleration is the derivative of velocity. So since that's a line, we remember that the derivative of a linear function is the slope of the line. So if we're able to calculate the slope of that line, then we'll know the acceleration from time equals 0 to time equals 8. So to calculate the slope of the line, we're going to use 2 points. So here I'm going to use the point 0, 4, and then I'll also use the point 4, 0. Remember, you can use any 2 points on that red line in order to get the slope. So here I'm going to do the change in y over the change in x. So I have 4 minus 0 over 0 minus 4. And that's going to give me negative 1. But let's talk about the units. So on the top, the y values, that was in meters per second. And then on the bottom is going to be our time values, which was in seconds. So if you have meters per second divided by seconds, you get meters per second squared. So the acceleration during the first 8 seconds is negative 1 meters per second squared. So since it's negative, that means that we are going to be decelerating or slowing down. Part C. During which times is the car accelerating, decelerating, and at constant speed? So we're going to be accelerating whenever our derivative of velocity is positive. And so the derivative will be positive whenever our function is increasing. So for acceleration, we want to know, when is this function increasing? So A for acceleration. So we're going to be accelerating. What looks like this is at 12. So from 12 to 15, that function's increasing. So we're accelerating from time equals 12 to time equals 15. And then again from 20 to 24. So again, I'm increasing here from 20 to 24. So time equals 20 to time equals 24. Now we also want to know when we're decelerating. So we're going to be decelerating whenever the slope of our velocity is negative. So here, the slope of our velocity will be negative when our function is decreasing. So that's going to happen from time equals 0 until time equals 8. That red line is the only part on this function where our function is decreasing, and therefore the derivative is going to be negative because it's a negative slope. So finally we have to figure out where we're constant. So we're going to be constant, put a little box here, we're going to be constant whenever our function is horizontal. So acceleration will be 0. So that means our speed is constant. So that happens from time equals 8 to time equals 12. We have this horizontal line. Again, from time equals 16 to time equals 20, we end up with this constant velocity. And then finally, from time equals 24 to time equals 30. So there were 3 places where our speed here, where our acceleration is going to be constant because our speed is steady. Part D. Suppose that at time equals 0, the object is at its home base. How far away from the home base is the object at time equals 4 and time equals 12? So let's draw a picture here to represent what's happening. So let's call this home base. So at time equals 4, let's see how far our position changed. Well, this is something we already calculated in part A. So from time equals 0 to time equals 4, if we look at the area under the velocity curve, that will tell me my change in position. So here we said that that was 8 when we did 1/2 base times height. And again, it was meters per second times seconds. The seconds units cancel and we're left with meters. So at time equals 4, we are 8 meters away from the home in the positive direction, so in the right-hand direction. At time equals 12, let's look at what happened. So we went that 8 meters in this direction, but then we turned around and we're going a whole bunch of meters back in the opposite direction. So we need to figure out the area between 10 and 12. We've already figured out the area before that, and then we can add those all up. So from 10 to 12, that's got a width of 2 and a height of -4. So that's another -8. So it looks like from 4 to 12, we have -8 plus -8 plus -8, which is -24. So I started off going in the positive direction, right? And I walked 8 meters. But then I turned around and I walked 24 meters in the other direction, which is 16 meters away from my home base, because it took me 8 meters to get back to my home base. And then I continued going. And so now I'm 16 meters in the other direction from my home base. So how far away am I from home at time equals 12? Well, I'm 16 meters away from home to the left. At time equals 4, I was 8 meters away to the right. So I'm able to find a lot of information using the fundamental theorem. And this is all really important because we're able to talk about the original function in a more succinct way.